As I said, z cubed minus 1, it is a difference of cubes, and we could certainly look to solve it like that. But I truly believe that once you get to anything cubic or greater, we might be looking, I think we might go to use de Moivre's theorem to solve, okay? And we've looked at how already de Moivre's theorem helps us to simplify complex numbers raised to a power, so that any z to the n can be written as r cis theta to the n, which is r to the n cis n theta. So we're raising the r value to the power of n and multiplying the argument by n, all right? And then once you've done that, so I guess to solve it, the process is write both sides in polar form, and then we equate the expressions, noting that the angle n theta is equal to theta plus any 2 pi theta, all right? So examples, I think, are the best way to go here, so let's have a look. So if z cubed is equal to 1, we can write z is equal to r cis theta, which means z cubed is just r cubed cis 3 theta. All good. So I can write r cubed cis 3 theta equal to 1. Now, what is 1 in polar form? Well, that's the same as cis 0, yeah, because that 0.1 is the 0.10, which is on the horizontal axis. So if I equate now, my radius, r cubed, is going to be equal to 1, which is the radius of cis theta. So there's my first expression or equation. And my angle 3 theta is going to be equal to 0, which is the equivalent angle, plus any 2k pi. So if I solve r cubed equal to 1, I get r is equal to 1, so the radius of all my solutions is 1. Theta, if I solve for that, divide both sides by 3, I can see that theta will equal 2k pi on 3. So then I just generate my argument angles. If I put k equal to 0, I get 0, which is the first one I had. K equal to 1, I get 2 times 1 times pi, which is 2 pi on 3. I could put k equal to 2 and get 4 pi on 3, k equal to 3 and get 6 pi on 3. And 6 pi on 3 is back to 2 pi, which is the same as 0. So not surprisingly, we get k values high enough, we go around in circles. Because we want my arguments to be within negative pi to pi, for every one you go positive, go one back negative. Okay, so I've gone one positive with positive 1. I'm going to go negative 1. If I put a negative 1 in there, I get negative 2 pi on 3, which is the equivalent to that 4 pi on 3 angle. All right. So if I do that, I get my 3 solutions: cos 0, cis 0, cis 2 pi on 3, and cis negative 2 pi on 3. Again, worth noting that if we just plot those points, cis 0 there, cis 2 pi on 3 out there, cis negative 2 pi on 3 out there, and those solutions are all symmetrical, equally spaced around my unit circle. Yeah, and that's going to happen when we use de Moivre's theorem to solve. Example 2, I've got z squared equal to 1 plus I, and we could try and solve with equating a plus bi squared equals 1 plus I squared, and sort of group terms and solve and those wonderful things. Instead, we're going to use de Moivre's. So if I put z equal to r cis theta, then z squared is r squared cis 2 theta. 1 plus I in polar form, well, the radius is the square root of 1 plus 1, which is root 2. The angle, tan inverse of imaginary over real, which is tan inverse of 1, which is pi on 4. Just check the quadrant you're in. The 0.11 is in the positive, top right quadrant, so pi on 4 is my angle. So if I put the two equations out, now I get r squared cis 2 theta is equivalent to or equal to root 2 cis pi on 4. So we equate the r values, so r squared has to equal 2 to the half, root 2. 2 theta is going to equal pi on 4 plus any 2k pi. So if I take the square root of both sides, r will equal 2 to the quarter. Let's tidy up my angle representation. I could just divide both sides by 2 there and get pi on 8 plus k pi. But I like to tidy up this right-hand side first by taking a pi on 4 out the front and getting 1 plus 8k. Yeah, so just check that in your head. Pi on 4 times 1 is pi on 4. Pi on 4 times 8 is 8 on 4, which is the same as 2 pi. So it's an equivalent expression. Now I'm going to decide both sides by 2 and get theta equal to pi on 8, 1 plus 8k. So again, substitute suitable values for k. If I put k equal to 0, I get 1 plus 0, so I get pi on 8. I can put k equal to 2. No, sorry, I can put k equal to 1, which means I get 1 plus 8, which is 9. So I get 9 pi on 8, which is slightly bigger than my principal argument domain. So instead, I'm going to put k equal to negative 1 and get 1 minus 8k, which will be 1 minus 8, which is negative 7, and get negative 7 pi on 8 as my other solution. And that's already within the domain that I'm interested in. So my solution Z1, 2 to the quarter cis pi on 8, or 2 to the quarter cis negative 7 pi on 8. Okay, so hopefully that's getting a familiar sort of ring to it. What have we got there? All right, last couple of examples. So we've got Z equal to A plus BI, where Z squared equals 3 plus 4i. Find the equations in terms of A and B by equating real and imaginary. So whilst I've just spent a couple of examples telling us how we know to use the modulus, we've been instructed this time to equate by using Z equal to A plus BI. So if Z equals A plus BI, well, Z squared is A plus BI all squared, which is A squared plus 2ABI plus B squared I squared, which if I group my real terms together gives me an A squared minus B squared, and the imaginary terms 2AB. All right. Now that Z squared has to equal the Z squared we've been given, which is 3 plus 4i. So the real parts have to equal, so A squared minus B squared has to equal 3. The imaginary parts have to equal 2AB has to equal 4. So there's my equations. Part B, which is just down below, says now solve. So if I solve, I want to solve A squared minus B squared equal to 3. So I might just take the 3 plus B squared across. And I've got AB equal to 2 if I divide both sides by 2. Yeah. Now if I square this bottom equation, I'll get A squared plus B squared equal to 4. And now I can substitute what A squared is equal to. So I end up with an equation an equation in terms of B squared. Expand and group terms, I get B to the 4 plus 3B squared minus 4 equal to 0. Now that's actually a quadratic expression in terms of B squared. So if we factorise that as if it was quadratic in terms of power, I'll end up with B squared plus 4B squared minus 1. All right, so I'll end up with a B squared equal to negative 4, B squared equal to 1. Now, even though we're in a complex environment, my A and B values have to be real numbers. They're real numbers. The B just happens to be attached to the I to represent it's in an imaginary direction. So B squared equal to negative 4 has no real solution, so there's no solutions in this instance. So I'm just interested in B squared equaling 1, which means B is equal to plus or minus 1. All right. So I'm going to substitute B equal to plus or minus 1 into AB equal to 2, which means A is equal to 2 on B. So if you substitute those in, we get those set of solutions. All right. If you substitute that B into the first equation, the A squared, you'll end up with a couple more plus or minuses. Yeah, and that'll give you far too many solutions. So in this instance, we need to be a little bit more judicious about what we substitute into because it's a Z squared, so there's only 2 solutions, which is why, to make sure we get the right 2 solutions, we'll substitute into the AB equal to 2. I think the final part said we then had to write it in factored form. So just be careful with taking your negative sign out. Okay, to get it into the proper factored form. Okay.